I am going to do now another example with hybridization and molecular geometry. But this time I'm going to draw another molecule. In the previous video I just drew allene, right? And when we did allene, this was the molecular geometry. This wasn't showing as much, and I had that. And the reason why this molecule was, I say this two hydrogens in this plane and the other in this plane, is because we have in the central carbon, if we number this 1, 2, 3, in the central carbon this is sp hybridized, and that here we will have, I'm not going to erase the pi bond because I'm drawing it explicitly, and it will have one pi bond to the side, and the other pi bond is perpendicular to the previous. So I'm gonna use it like that. And because of that, now the hydrogens, notice if the pi bond here is in the plane of the board, the hydrogens are perpendicular. And happens the opposite to the other side. So it turns out that this molecule then is three-dimensional. So we have hydrogens in two planes, this plane and this plane. But now I'm going to draw another molecule. So this is, let's do it the formula just here. Now I'm going to have this molecule, and here we will have two hydrogens. This molecule is actually called ketene. This was allene. Right. And I'm going to draw that molecule now. Again, because the central carbon is bonded only to one atom here and to another atom here, I need a speed hybridization here. Also, I see that there is a sigma and a pi bond, and a sigma and a pi bond. That means that I need to have in the central carbon two p unhybridized orbitals. And I'm going to go with the drawing. So the atoms now, first, I'm drawing sigma bonds. And as I said, in the central carbon, this is sp hybridized. So if I have one sp orbital in this, forming a sigma bond here, in another in this direction, so linear, we will have one p unhybridized orbital here, and the other will be perpendicular to the first. So now I have my, in the line, the two sp orbitals and the two p orbitals, one to one side and one to another side. Now, I want to make a pi bond to the carbon here. And to make a pi bond, I need to have a p orbital here. That's my pi bond. And now this carbon has sp2 hybridization, sp2, and I have, this is my p unhybridized orbital, and because this is in this plane, now the sp2 orbitals forming the bonds to hydrogens are perpendicular to the plane of the board. Again, pi bond is here, the hydrogens are in the other plane, like that. And then what's left is now I need a pi bond with the oxygen to the other side, and then I'm going to say the oxygen is also sp2 hybridized. Here's my pi bond. And now notice that I have two lone pairs here in the oxygen. Since this is sp2 hybridized and the pi bond is like that, the sp2 orbitals are going to be in the plane. So I can draw a line, but now this is occupied by the lone pairs. Now this is same by drawing with the orbitals. Here, this is a sigma bond that is now formed by the overlap of an sp orbital from the central carbon and an sp2. And this sigma bond is also formed by the overlap of its sp orbital and one sp2 orbital from the carbon on the side. And I will have pi bond, pi bond. These electrons are now Notice in sp2 orbitals, they are in sp2 orbital in the plane of the Bohr. Pi bond is like that. Now, notice that this time, all of the atoms are in one plane. For the molecular geometry, we don't take into account what are the electrons. The orbitals here are filled with electrons. Here we had atoms, and we had, in the example of allene, atoms in this plane and atoms in this plane. Now, I only have atoms in the plane that's perpendicular to the Bohr. So this molecule is actually planar, ketene, even though we have the same type of orbitals. But we don't have atoms here. We just have lone pairs. So molecular geometry, here it was, in the case of allene, is 3D. Now this is planar. And we be doing more exercises in another video.